Okay, so I'm debating with myself. We already had a quiz. Will it be too much quiz if we do it today again? Okay. I don't see enthusiasm. Why don't we get started? We can do it again. I think it's pretty obvious who attend the class, who don't, and how everybody is doing in the quiz. So I looked at the quiz last time. I think most of you had a very good understanding about lattice theory. So what we did in the last lecture is go in further and cover what is Flory-Huggins theory. And if you know the lattice theory well, it's not that difficult to go from lattice theory to Flory-Huggins theory, right? So I think the major difference is that we need to understand there is a entropy issue within your polymer connectivity when you consider in the Flory-Huggins theory. If you knew that key concept, I think you should know pretty well. The other part that we covered in the last lecture is actually about the Flory-Huggins parameter. And I like to give the students, in terms of importance level, that is like the MVP in any football games that everybody can comprehend. It's like GOAT for polymer physics. GOAT, this guy, right here. Okay? He's like as respected as Tom Brady in the football field. So if you don't know other names, but at least you need to know this guy in polymer physics. Flory-Huggins parameter is kind of the beauty of the polymer physics. I'd like to emphasize again. That very simple parameter chi summarized all the polymer interactions between different species, polymer solvent, etc., and that will help you to understand what is the phase behavior and mixture in your polymer solution. Okay, so what we're going to do today, we have covered everything about Flory-Huggins. You should know that how does the chi parameter and entropy impact the mixing in the polymer in a solvent case or in a polymer case. And apply that knowledge, you should have a relatively good understanding about why polymer solvents sometimes are harder to mix compared to solvent, or even extreme cases when you mix two polymers in the melt, it's quite challenging. That's why challenge/opportunity in polymer engineering is finding compatibilization for plastic mixture. If you want to mix polystyrene, propylene, they're not likely to mix. So you need to do some treatment to it. That gives us an opportunity to talk about the polymer physics class. Okay. So today's lecture, we're going to chat a little bit more about what is Flory-Huggins parameter. We kind of defined what is chi is. And we chatted a little about what the significance of the chi value. So today we're going to go and explain next 10 minutes what the chi parameter are historically used and what the values are and what the limitation when you define a chi parameter for all the thermodynamics in the polymer physics. After that, we're going to go into talk a little bit about osmotic pressure, and it's a natural extension about what we talked about chi. So Flory-Huggins parameter chi is a way to you measure the polymer solvent interaction. Okay, that is very useful. So next step is when you want to consider how do we measure this chi. There are several ways we can do that, and there are several ways you can tie a chi parameter to another parameter we're going to discuss it today is called the second viral coefficient, is relevant to this osmotic pressure. So let's get started for today's part. We already did this part, so I don't need to go into again. This is an example when we talked about what is mixing. So here is a recapture of Flory-Huggins parameter. So chi parameter is basically generalized to describe any binary interaction. Let's say we talk about chi, we consider it is a chi between two materials. It can be a chi of polystyrene versus polypropylene. But is it the perfect parameter to describe? Apparent answer is there is some limitation for the theory. And what are these limitations? So first, it's a binary parameter. So what that means, we only consider, generally speaking, what the A and B's are. But we missed out some of the other parameters, such as cis-trans content, molecular weight, temperature, etc. These are also affect the chi parameter. So the mixing of these, in the mixing we simplify the problem. So those effects are not considered. However, it's still a pretty good parameter to predict a lot of property. In this part we already covered, entropy is always going to favor mixing because the entropy or the disorder degree going to be increased after we mix it. So chi parameter is actually predict if the composition will mix or not. Okay, it's a battle. It's a tug war between the entropy and enthalpy. So we already briefly talked about when chi is equal to 0. There is some additional fancy term called ideal mixture. There's no energy associated with the interaction. In this case, enthalpy is equal to 0, then entropy is always going to favor your mixing, okay? If chi is positive, mixing is opposed from enthalpy perspective, but they still need to go through a competition between entropy and enthalpy. So mixing is opposed by chi, but it needs to be considered as a whole. What is delta G for the system? If it's negative, it's always going to be promoted, okay? Since the adage of like dissolves, prefers the like is frequently true, what that means is you can look at solubility parameter and predict the chi. But generally speaking, most of the values are positive, chi. So we will fill into this range, and you need to determine what the chi significance of the chi value or enthalpy value with respect to the entropy. Okay? There's a few exceptions that if there are a lot of interaction between species, then chi will be negative. This applies to non-covalent interactions if you have in your material. It will promote mixing, such as hydrogen bonding within your molecular, etc., etc. Okay, this is a little bit a busy plot, but my point is just to show you what are the handbooks you have and what you can look at. You can read what the chi parameter with respect to different solvents, with respect to different polymer. So in this case, you can look at the polymer handbook. This will tell you at this temperature what the chi parameter for this particular polymer in this solvent will be. You can see the chi values can be somewhere between 0 all the way to as high, for example, in this table, 0.63, etc. So you do have different interaction with different solvents. I want to go into too much detail, but this is available in either the textbooks or polymer handbooks you can look at. Okay? So the last but not least, a few minor points about limitations. First is in the theory, when we talked about it, we made a few assumptions, right? When we talked about lattice theory, we talked about how lattice distance, lattice parameter plays a role. So we didn't consider temperature effect, chain length effect, and composition effect, etc. So in reality, chi parameter is typically a temperature-dependent parameter. We typically call it chi effective chi. So at the chi at different temperature, U will equals to, can be generally described A plus B divided by temperature. Okay? So so how does this impact or chi dependent on temperature? If temperature raises, this T will increase. Then the value of chi effective will depend on if B is a positive or negative term. If B is a positive, when we increase the temperature, your chi will drop. Okay? But if the B value is negative, you would have increase of temperature raise the chi parameter. There is a significance in the sign of B we will talk about later if it's more pertains to phase diagram where if your temperature goes up, your chi goes up. One of the effects could be at low temperature, your polymer is mixed. But at high temperature, your chi increases, its phase separates. So we could have a LCST behavior, or we will describe more detail, lower critical temperature phase behavior. Here is a few other parameters we describe. Okay, what is the generally an A and B value for a range of the polymer? So PS, PMMA is commonly known, right? This is everybody familiar with. This has a value of 0.0129, indicating there's some attractive force, repulsive force in the A. A is a constant, right? Then B is a positive value. So when the temperature goes up, the chi parameter between the PS and PMA will drop. If the chi drops, which means they are likely to be mixed, so a way to promote the mixing can be relevant to heating the PS, PMMA up at a relatively higher temperature. Okay, it also tells you the temperature range is measured. So this gives you some useful information. In this scenario, we also see what is the DPS means. D means deuterated, okay? So when you're doing neutron scattering, you will see people do deuteration. And one of the effects of deuteration is it will change the scattering length density. It will change contrast. But you will see once it's deuterated PS in normal hydrogenated PS has a very low chi parameter. A is low, B is a relatively high value. But this is if the molecule were high enough, you can still have phase separation. A couple other that once you raise temperature, it will show different signs. For example, DPS and PPO show the negative B value, which means when you heat up, it will phase separate. When you lower down, it will phase mix. Okay, likely. What's the other limitation is the volume effect is we haven't chatted too much. We assumed when we are mixing, there's no volume change on mixing, which is not necessarily true. For example, if you mix two solvents, it might have 1 + 1 less than 2 because there's voids in molecular volume. It can change in mixing in the volume. So there is a minor effect in the volume we could consider to crack the Flory-Hagen theory. There's also free volume effect. This would also impact our idealized model of filling the lattice. You could generate that void that is not filled. But generally speaking, chi we should treat as dependence of two material, but also dependent of also on the temperature. Don't think it's a constant if you already determined what you want to mix. Okay, if you choose polyethylene, you can still do something to modulate its chi effective value. So next, we're going to shift a little bit gear to talk about osmotic pressure. So first is what is osmotic pressure? So can someone help me out here when we talked about osmotic pressure, what it means? Please, yeah.
Force of flow between two gradients, or the flow between two gradients of concentration?
That's pretty good. So fundamentally, yes, but we typically use a term called chemical potential. So let me describe what μ10 means. Chemical potential is another term that relevant to the thermodynamics. That means how much potential that your material holds. So if we look at it here, you can think about if we have a chamber that has two sides, as described here, and all these tiny gray dots are solvents molecules. This is idealized membrane, and this membrane does one thing. It allows the solvent to pass, but not the polymer. Polymer is too big to pass through this pore. So it's created an interesting phenomenon that if we put two let's use some real example. That's probably easy. Toluene, polystyrene, you dissolve it. There's a membrane in the middle. Then you would expect to observe that if there's a capillary here, there's going to be slightly taller and in one side where you have the polymer there. So that tiny highlight here in yellow is relevant to osmotic pressure. Okay? So what this means is the pressure in this side is slightly higher because of the presence of the molecular. At the first glance, it may not be much tied into chi parameter, but we will talk about it in this lecture. It's actually very relevant. This is another way you can understand how your polymer interacts with solvents with respect to this osmotic pressure. So we're going to address two questions. Since I mentioned osmotic pressure, of course it will be useful for us to study and must be tied into some parameter we talk about polymer solution. So what is it? We're gonna answer this question. The second question we're gonna answer today is why we have this osmotic pressure to happen. Okay? So we observe the phenomenon, we're gonna explain why, and we need to understand how we can leverage this property to meet the need we want. In other words, to measure polymer solvent interaction. I'll speak about the application first because that's most easy to understand. And I think we want to dedicate everybody's attention to the most important part. So what osmotic pressure can do for us? Any guess?
Use it to check number molecularly.
That's one of course important application. Although nowadays I think this technique still could do that, but nobody is doing it just because it's not as efficient as other techniques such as light scattering, etc., steady light scattering, GPCs to determine the molecular weight. But yes, that's absolutely one of the applications we can use osmotic pressure. Get molecular weight for your material. Because molecular weight will tell you how much rays it has. By looking at this tiny yellow piece, you can see how much osmotic pressure. Other thoughts, how we can potentially leverage osmotic pressure for? Let me tell you a little bit. It's apparently is a very good parameter to understand how your polymer interacts with solvents. Okay? So if the polymer can be strongly interacted with solvent or weakly interacted with solvents, can be measured and determined by a very nicely designed osmotic pressure experiment. Thanks, Jeff. So let's close the door. It's a little bit noisy. But solvent polymer interaction can be nicely measured then, like we talked about Flory-Hagen theory. Remember, what's the other parameter we talked about can determine solvent polymer interaction parameter? That is chi. So osmotic pressure can indirectly tell you what's the chi value for your polymer. Okay? That's why we want to put it here and understand how we can take advantage of this interesting phenomenon to determine what is potentially chi value. Although we don't call it a chi, we call it a secondary coefficient in osmotic pressure experiment, but they are very relevant. Okay? So with these two information in hand, we know this is useful. So now let's talk a little bit about it. We're going to go through the reason why this is actually happening, this phenomenon. It's a little bit, requires a little bit second law of thermodynamics. So bear with me. If you have some difficulty understanding the thermodynamics, you can always ask me questions, stop me in the middle, okay? So let's first understand what is chemical potential. So chemical potential or osmotic pressure tells you that the partial energy in this for this polymer is different between these two. So in order to compensate that, we need to consider to draw some of the molecular to reach this equilibrium. Okay? think about that. That's concentration for the solvent. There's a gradient here and there. Now consider the polymer. Or you consider polymer, that's fine. You want a polymer to diffuse there, but it's impossible to go there to reach equilibrium. So you need to draw a solvent from the other side to dilute it. And that's a driving force. If you don't have any increase, if you don't have any this raise of pressure, this will be a spontaneous process happen until it reaches a concentration equilibrium. There's no difference. And you know that means there's always going to solvent. But in reality, it will stop at a few amount of molecule diffuse here, because the pressure will give a negative force. When there's pressure, it will want to push the molecule back. So there's equilibrium going to be strike when solvents want to go there to compensate the chemical potential difference, and there's a pressure that draw back those molecules to the other way. And this equilibrium will be met. Okay? So this equilibrium will tell you what is this osmotic pressure is. That's a pressure that's going to be pushing to this chamber from left to side. Okay, then there's pressure coming from the other way, and these two pressure will be equilibrated. Okay, any question for this part? Okay, if not, then let's take a look. This is a lot of thermodynamics equation, but bear with me. What we are looking at is very simple. First, on the top, it's very generic description of what is delta G. G is a free energy. Okay? In the previous lecture, we always talked about how the system's free energy depends on entropy multiplied by temperature. So here, dG, this D letter in front of means derivative. Okay? Derivative of free energy will depend on S, partial derivative of temperature, plus V dP. So what is the first term? That describes the entropy. Second, V dP describes how much work you did in the system. Work is pressure multiplied by volume. That's equals to the work. Okay? Or the last part is chemical potential. Chemical potential is defined by mu chemical potential dNi. Ni is a molar volume. Okay. Sorry, the molar, not volume, molar. Okay, how much moles of molecule is there? That's Ni. So in here, we are just trying to tie how does the partial volume of the volume can be dependent on the chemical potential with pressure. Okay, this can be very straightforward. How we ties into here is using this partial derivative. So at a constant pressure and a constant n, we can know that free energy will be a partial derivative of temperature, because dT multiplied by S will be equals to dG, as shown in top. We just break this top into 3 sections. If we take partial derivative of dP, G dP, at a constant temperature and Ni, if T is constant, this will be 0, and this will be 0. So that's why we can write this. So this tells you free energy is dependent on entropy, volume, mu at different partial derivative condition. Okay, the next is purely a mass trick. What the mass trick is, we are trying to link partial volume to partial molar and chemical potential to pressure. And we will reach a conclusion that they can be tied together by considering the second derivative of delta G. Delta mu, delta P is given by here. Let me see. Delta mu is basically given by right here. So it will be equals to delta G divided by a partial derivative Ni, which we can apply. And you can equals to another partial derivative of P as shown here. And we can switch back and forth. We can take first partial derivative Ni, then Lp, which we'll rewrite. We basically flipped them. That's allowed in partial derivative. And now if we do a delta G, delta N first, this delta G, delta N, delta G, delta P will give you volume. Okay, delta G, partial derivative delta P. So the right half will give you delta volume. As I mentioned, there looks complex, but in a nutshell, we're just trying to link volume, partial derivative versus chemical potential, because osmotic pressure is relevant to partial derivative and chemical potential. So now we will give you a generic relationship between how does osmotic pressure dependence on molar volume xi. So this gives you how does chemical potential with linked to osmotic pressure. It tells you it will be equals to constant temperature, constant P, and partial chemical potential divided by P and multiplied by dP. So if you have a change of concentration from left versus right side, you need to meet the condition here. We consider the partial vapor. This is a osmotic pressure that at the center of this, it needs to reach equilibrium. The chemical potential, regardless the solvent, will be equal to chemical potential plus this osmotic pressure. So it equilibrates in terms of pressure. Okay? So we can simply write out the equilibrium states as here. This will be left side of the chamber. This will be equal to the right side of the chamber, which is partial molar pressure plus osmotic pressure multiplied by VI. Okay, if we switch a little bit, considering hold what is the osmotic pressure and move the partial vapor pressure to the other side, we can reach the conclusion pi VI will be equal to mu 0,1, which means partial vapor pressure, partial osmotic pressure on the left side minus the other side will be equals to minus RTLA. And this is given by delta G, a general equation here. If we further expand it, A1, in our case, it's going to be equals to roughly X1. X1 is how much polymer concentration in your solution. So we can link how much osmotic pressure you had with how much polymer concentration you had. Okay? The higher the concentration, you will generate increased osmotic pressure. So now we can do one more step to further expand this particular relationship, because law in turn is not straightforward to do. We did it in several other examples to do a Taylor expansion. So a Taylor expansion basically assumes that when lawing 1 minus x, when x is very tiny, it will be equals to minus x. So this is a mathematical approximation for this particular term. If we apply here, osmotic pressure, unit volume, R is the gas constant, T is temperature, lawing 1 minus x2. You can rewrite such that the second term, lawing, can be simply replaced by minus x. Of course, this approximation is, this we only consider the first coefficient of expansion. If we consider second coefficient, we're just going to talk about at the below, okay? So this will allow you to reach this conclusion. Osmotic pressure, you can rearrange it. Minus RT will be equal to X2 V2. X2 is the concentration of the, in this particular case, it's going to be solvent. Polymer, not solvent. V1 is unit volume. Okay, how much like unit volume for your material. This is a constant. RT, if it's fixed, is constant. So the higher the concentration, the higher the osmotic pressure. So if I, let's say, prepare a 1 gram per mil versus 2 gram per mil, I would expect to raise in that lensing osmotic pressure. So this only consider the first expansion, but if we consider high order terms, we will reach the same. This would be, again, the first term, just some mass. Ln 1 minus x will be equals to minus x plus a constant and x2 squared divided by 2, and plus the third order term. Why we can just approximate to the first term? Because if x2 is little, let's say it's 0.01, x2 term will be much bigger than x2 squared. 0.1 multiplied by square will be 10 to the minus 4. So we can safely sometimes eliminate the higher order term. However, we kept the second viral coefficient and third viral coefficient for the discussion here because they will make a difference, as we will show in the next slide. So let's summarize what we find in applying thermodynamics in rearrange and connecting the partial volume in terms of osmotic pressure with respect to the concentration. So this is the first time we already discussed the thing here. That says osmotic pressure will increase with concentration. And there's a higher order term that depends on the value of A2. If A2 is positive, then you will see this is going to be y equals to ax squared will be a parabolic term, right? Despite A2 might be small. Then A3 will be another even higher order term. So let's go from the theory to some real data. I'll come back to this slide just in a second. I want to show everybody this particular plot first. Some real data, okay? So this is what people measured in a polystyrene cyclohexane. This is measured osmotic pressure in 8 atmosphere, or that's a unit of pressure. So this is concentration of your polymer. There's no question that osmotic pressure always is going to increase with concentration. So what we did is, in this example, we show that you can measure at different temperature. Let's look at 20 degrees. You prepare the polymer solution, measure osmotic pressure. Next one, you just put it in different vials and measure the pressure. And the beauty of this measurement is fairly simple, right? I think if I tell my 5-year-old just to measure a 5 gram of table salts and adding 2 ounces of water, he can do it. So it's typically the same here. When you measure the polymer, you add in solvents. You can now use the apparatus to measure osmotic pressure. The application of that is not plot as pi RT, because pi RT will depend on concentration. If you move here, you can get pi divided by CRT and equals to 1 divided by molecular weight. So the intercept of this pi divided by CRT will give you the molecular weight of your polymer. And it will depend on A2 multiplied by C. Now, A2 will tell you the quality of solvents, actually. When A2 is equal to 0 or almost flat, that means it's a Theta solvent. A2 is positive value, that means you have a good solvent. A2 equals negative value means your solvent quality is not good. So that's the beauty of osmotic pressure, how you can use that for determining the quality of solvent. Okay, so let's take it back one step. Let's come back here again. So what we are trying to show here? What we are trying to show here is to convert X2 to concentration. How does X2 which is a number or a molar volume to a concentration. Anyone can help me? How do you connect those two? Number of solvents in the mixture to concentration of the polymer in the mixture. You need to know the molecular weight of your polymer. And you need to know the other part is the unit volume of your polymer. Okay? So what we're trying to show here is in the lab, we actually going to determine what is C2 concentration. Concentration is determined by how much mass you have divided by how much volume. All right? So in the dilute solvent condition, we don't need to consider how much polymer occupies the volume. Let's say 1% polymer. You can take an approximation. Just consider how much mass you had for your polymer divided by how much volume in total. We can now connect the mass to the molecular weight. Molar mass, this is the number of moles, N2. Then you can basically safely reach C2 will be equals to N2, how many moles of the polymer, N2, molecular weight of the polymer, divided by V1. V1 is the volume of the solvent. And V2 we already eliminated there. We now have a way to link how many moles of your material to how much concentration. And we could additionally get the molar volume with respect to how much how many moles of it. So in the end, what we could reach a conclusion as showing equation down below, X2 molar volume of polymer equals to V1. What is V1? V1 is the unit volume of the solvent molecule, or the lattice sites, how much each lattice are. It's a constant, okay? Once we define, this doesn't change or depend on how you count your system. C2 concentration is what we can measure, we can prepare. N2 is molecular weight of your material. What we do now, apply what we learn, how we can link X2 and C2 in osmotic pressure equation. We can reach osmotic pressure divided by RT will be equal to the first term. It's going to be C divided by N. C is concentration, okay? And A2 C squared. This is a generic term. A2 is defined as a parameter we call second variable coefficient. And this second variable coefficient is basically covers a lot of information about how your polymer interacts with solvent. And you have even higher order term, A3. In normal cases, we didn't consider this A3 because it's dependent on C3 or concentration cubic. And this is a weakly dependence. We typically only consider the first two in real experiment. So we already see an example. Pi osmotic pressure divided by RT. These are constant. If you know the temperature, you know that. You already cover. You can prepare the sample at different concentration that measure osmotic pressure. You can back calculate that molecular weight out. How you plot it should be osmotic pressure normalized by CRT. C is concentration. If you take 1C to this side, this will be equals to 1 divided by N. This will be equals to A2 plus multiplied by C. Okay? So this is how we get to this particular equation. I think we went pretty fast, so I want to leave a few minutes for questions. So everybody get how osmotic pressure can be used to get molecular weight and second variable coefficient here. Any question? Good. I'll give you a little bit of time to digest what we just said. So how we understand now all the parameters except A2 is a little bit abstract. So fundamentally, A2 comes from the expansion we did at the low concentration, right? So we consider the higher order term here from pressure dependence law in 1 minus x2. And when we expand this particular term, the higher order term is basically this one, A2. What is encoded in this beautiful A2 is many parameters. This A2, as I mentioned, describe two body interactions, one polymer molecular and solvent, and it describes how this interaction is behaving, okay? This can be attractive interaction or repulsive interaction will be reflected. And we will learn when A2 is positive, it says it's good solvent. That tells you chain will expand like we learned in the last lecture. A2 is negative, that means poor solvents. Chain will collapse or precipitate. And A2 equal to 0, although I didn't write on the board, as you can see, there means the chain doesn't depend on its interaction with solvent. Or equivalently, that's a definition of zeta solvents. Thank you. Okay? And A3, which is three-body interaction, multiple polymer solvent interaction, because it's much weaker dependent on C, we typically don't consider that. Okay? Because imagine C is typically, when we measure, it's very dilute. 1 mg per mil. So C to the cubic, you won't see much influence on your material's property. A2 value also depends on what is the temperature effect. The polymer solvents interaction changes what is A2. So for example, this A2 can change depending on low temperature to high temperature. Okay, so when you describe A2, the temperature is a big factor. How it modulates how your polymer interacts with solvents. We also cover roughly what is the zeta solvent, and that defines basically your polymer adopt a random color condition. So here is an example how several polymer and their zeta solvent and zeta temperature. So for example, polyethylene, biphenol at a relatively high temperature, or polystyrene in cyclohexane and 33 degree is a good example. Give us ability now to measure or do polymer physics experiment at the zeta condition to test what our theories are. But in reality, how you get this zeta solvent can be done by osmotic pressure. You just need to measure, like we show here. I'm going to jump it again. Put a polymer in a solvent, measure osmotic pressure, modulate temperature. It will change the interaction between polymer and solvents. Then go back to look at the slope. When A2 is 0, you can get this will be the zeta condition for polystyrene cyclohexane, roughly 34.5 degree. Okay. At the low temperature, it's a bad solvent. At the high temperature, it's apparently a good solvent, as this slope is larger than 0. Correct? So let's look at here. So membrane osmotic pressure needs to be measured at very low concentration. Why? Already explained. In the expansion of that mathematic form, we need to eliminate higher order A3, A4, A5. We need to consider C to be low, concentration to be low, so that C cubic is smaller, much smaller than C squared. In such that we can eliminate C3 terms, so that we can plot osmotic pressure normalized by concentration, R, and temperature, or sometimes you don't put temperature there, that's fine. And plot it with concentration. And it will give you two interesting parameters that are useful. You can measure the intercept with the y-axis. These are your measurement data points. You can get the intercept. The intercept will be equal to B, or 1 divided by molecular weight. And the slope is basically A2 parameter, or given by here, your secondary coefficient. Okay. Or osmotic pressure is measured by an instrument. The other two parameter you can just calculate. Okay. And we already see a good example how you can use that to calculate. So in this slide, it basically says secondary coefficient can be measured and compiled quite nicely. And I will talk about in the next lecture, if you get a feeling that secondary coefficient actually also covers how your polymer and solvent interacts. And if you remember in the Flory-Huggins parameter, the chi parameter also discussed how your polymer and solvent interact. Are they lost brothers many years back? You would have guessed it must be, right? They describe the same parameter, they look the same to me, so they must be at some point talking about the same thing. I'll leave that as a homework for everybody to think about. Not necessarily homework, but the home question for everybody to think about. How chi and secondary coefficient might be linked to each other, or are they actually talking about the same thing? So here we cover a little bit to the tail end. How about when we need to consider the third vary coefficient? The third vary coefficient in the last two lectures we didn't talk about, right? So in that case, we divide by osmotic pressure divided by concentration, plotted as concentration. It should be a linear. But in some of the data, if you look at some of them here, it's linear, then it starts to deviate, right? So if you look at these, looks fine, but particularly for this curve, it's clearly turning up. There's an upward trend. So why? And what's happening to that? And if you see a deviation at high C when you plot the osmotic pressure divided by C versus C plot, remember we eliminated the high concentration term. So this upward turn coming from the dependence of A3. So effectively, this equation should be right. Osmotic pressure divided by C RT equals to 1 divided by N multiplied by A2 multiplied by C plus what is missing is A3 multiplied by C squared. Right? Now you know y equals to A3C squared will take a parabolic turn. So that's why sometimes at high concentration, you will start to see this upward trend. And high concentration, for example, this applies to 10 milligrams or higher or more than a few percent. Okay? At low concentration, you can safely eliminate a higher point. And again, this is you can see this is a higher slope. A2 is larger than 0. This is certainly a good solvent. So this is almost a flat. So we can call it marginal solvent or closer to the theta solvents, same as we described. Okay, so I should not show this slide because that is what we're going to talk about in the next class, is how do we link. We learned everything about osmotic pressure. It's a useful technique, simple to use, help you understand molecular weight and interaction of your polymer with solvent. So why we talked everything about Flory-Huggins, then we jumped into here. You remember in Flory-Huggins theory, we don't have a way to quantify chi. Osmotic pressure can measure A2. If we somehow can find the relationship, those lost brothers, between A2 and chi, we can actually find a way to measure this chi parameter. If we can measure A2, then we can get chi, then we can get a lot of useful information. We can now construct a nice phase diagram So I want to wrap up today's lecture here. And in the next lecture, we actually will talk about, if there's a link, what are they, and how can we use now what we have learned so far to go one step further, going from just on measurement to prediction. What I mean by prediction is now if I give you a polymer, a solvent, a chi parameter, I want you to be able to tell you will they be phase separated or not. That will be quite a useful outcome for the polymer physics class, thermodynamics, right? So we're going to take a break now. For this Thursday, we're going to come back and learn about how can we use what we learned so far about interaction parameter and to predict a phase diagram. Okay? With any question for today's lecture so far? Okay, if not, then feel free to drop by my office to ask me about office hour question. Otherwise, we can finish today's class.